right, guys, so welcome to chapter 15, part 1. I am going to split this chapter into two parts. The first part is going to deal with an operation called the dot product, and the second part will deal with the operation called the cross product. So, okay, in this part 1, we're going to talk about, again, this idea of something called the dot product, and we're going to talk about what it can do, and that'll be both in 2D and 3D. So, the dot product can be used to find angles between vectors. It can also be used to find projection of vectors, and then the distance between points and lines and points and planes. We might also get to something called work in there, which you might have talked about in physics, so that might also be something that we get to see a little bit of. Okay, so first off, I know that this is a little overwhelming to look at this page, but don't. We're going to break it down. So first of all, we're going to come up with we want to find a relationship for the angle between two vectors. Okay, so I have a drawing ready where I have 2 points, A and B. Okay, and I've drawn vectors out to A and B, and I've also labeled the points. Okay, this theta is referring to the entire angle between the two vectors. Okay, so we are going to use the idea of finding the length between A and B to relate this angle. So if I were to draw this length between that little segment that goes between A and B, you should remember how we were able to relate this angle and this side and these side lengths of a triangle from way back in first semester. Do you remember how we related those? If you guessed law of cosines, you'd be correct. So law of cosines allowed us to relate sides and angles within our triangle. So let's do it. So law of cosines said that the side opposite the angle we're going to use squared. So now this side would be the magnitude of this vector that connects them, right? That's the length. So that's what I've got here, squared. So, that side squared equals these two legs length squared. So I've got magnitude of A, so we're just letting that be little a, and then the magnitude of B squared. So again, opposite side squared equals leg squared plus leg squared minus 2 times the length of this leg times the length of that leg, cos of the angle. Okay, so this is our law of cosines. All right, so then this is just a lot of work. I just showed it so you could follow along. So this is me finding, the magnitude of AB and then squaring it. Now remember, magnitude is square rooted. So when I square root and square, that's why you don't see the square root here. So I've got my change in x squared, change in y squared, change in z squared. I have these two guys, which again, because I'm square rooting and squaring, you don't see the square root. These two guys are not squared, so that's why you see their square roots there for the magnitudes, and then of course cos theta. So over here, I actually did the squaring and added everything up. And then over here, I've got some values. I brought those across, which actually canceled some of my stuff out and left me with just this guy equal to that. Then, of course, I'm going to divide everybody by the -2, which gets me down to something even a little bit nicer. And then my last step, if I wanted to get the angle, would be to divide by this coefficient here. And so I'm at this point. So notice, guys, I was able to get this relationship all the way down to this. Okay. And then this relationship can also now be written as, this got a little transferred a little funky, A dot B over, now I don't know if you guys noticed this, but this is the change in x from that first vector squared plus the change in y plus the change in z square rooted, which should look familiar. That's just the magnitude of A. So I've got magnitude of vector A times magnitude of vector B. Now I could put a little dot here if I wanted. I'm not going to because I think it might confuse you. And once we learn more about the dot product, you'll be able to discern that for yourself. So for now, I'm going to leave it out, but it is just multiplication on the bottom. Now this little dot symbol is not multiplication like you're used to. We redefined it. This is right here, this symbol, when it's two vectors, this is called the dot product of two vectors. And so the dot product is this. So let's look at what that is. That means that to get the dot product of two vectors, you have to multiply a1, b1. Well, let's look at what a1 and b1 are. a1 is the change in x, and change in x. So we're multiplying the change in x's together and then adding, let's see what this is. That would be the change in y's of my vectors together plus, oh, the change in z's. So basically you're taking the product of the change in x's, the change in y's, and the change in z's, and then just taking the sum of that. That is the definition of a dot product. So let's take a look on the next page. So again, this should say dot product. Okay, so this is the dot product. This is another way to say the dot product, and here's why. If we just go back real quick, if I took this, guys, and multiplied both sides by the denominator, so if I just moved these guys over by multiplication, then I would have the dot product by itself. So that's what I've done here. I've isolated the dot product by itself. So the dot product can either be found doing this, or the dot product can be found doing that. So let's look at the differences. So if I've got vector A, so I'll call this vector A, maybe that vector is 1, 2, 5, and I've got vector B, guess I'll do this. And I've got vector B, which is, maybe -3, 4, 0, okay? And I wanted to find their dot product. Then remember, if I've got the vector components, then I can do this version. So this version would say multiply the x's, so the change in x's. So my change in x's would be -1 times 3, plus my change in y's are 2 and 4, and my change in z's are 5 and 0. So I end up with -3 plus 8 plus 0, so 5. So my dot product would be 5. Now, if I knew the length of these vectors and the angle in between them, I don't have the angle labeled here, I could also find the dot product. I could just take how long this is times how long that is times the cos of the angle in between. So it's just that there are two different ways you can do it. I said in mathematics, we mostly do work with basis vector form, so we tend to use dot product using this left-hand side. But in physics, you're more likely to see the magnitudes of vectors, which are like their lengths, and the angles between them. And so you're more likely to compute dot product using this relationship, which is totally fine. Both of them, in this case, would give you a 5 if you knew the angle in between. Okay, so this is brand new, guys. This definition of dot product, we just defined it. We use it so often, this idea of finding and relating angles in that triangle with vectors, that we have come up with a rule for what dot product looks like. Okay, so what are some properties? If I dot a vector with itself, I basically just get the magnitude squared. You can easily prove that. Dot product is commutative. You can do the same. It'll get the same thing forwards and backwards. Here you can see that the dot product is distributive over addition. So you could do that. And then also here's some associative stuff with some scalar multiplication. This last one, this is the zero vector, guys, which is just 0, 0. So they're saying if you dot that with a vector, you're going to get 0. Basically, you're not going anywhere. Okay, what can we use the dot product for? Okay, so one of the first really cool things that you can use it for is testing whether vectors are perpendicular. So I'm actually going to make this a little bigger and go down. So here's what I want to show you guys. We just looked at the previous page and looked at dot product. So I'm going to use the one where it was the magnitude of vector A times the magnitude of vector B times cos of theta. So remember, if these are two vectors that meet, so imagine that these vectors were actually perpendicular for a second. Okay, if they're perpendicular, then that would mean the angle between them is 90, right? So if this relationship is true for dot product, which it is, then to find the dot product, I would take the length of A times the length of B times the cos of theta. If that theta is 90, you guys remember what the cos of 90 is? Yeah, it's 0. So that would make this whole thing 0 no matter what the lengths are. So if your dot product comes out to be something that's 0, you know that the two vectors are perpendicular. That's awesome. The reason that's so nice is we have been working with perpendicular vectors in 2 space pretty easily. Like if you have a vector in 2 space and you want to find one that's perpendicular, not a problem. Perpendicular vectors in 3 space have been really difficult to find. We have to find like a perpendicular plane and then find the point where the line intersects the plane. I mean, it was tedious and we could do it, but now we have a way to test or find vectors that are perpendicular in 3 space in a quick way, which is, does their dot product equal 0? Okay, so that's a big, big idea. That's something you should definitely have down in your notes. Vectors are perpendicular if and only if their dot product turns out to be a 0. So obviously, vectors can be perpendicular, many vectors can be perpendicular to a given vector. So like if I have this vector, I can have a vector that's perpendicular in this direction. I can have one in this direction and it's really long. That's why there are basically infinite ways to get vectors that come out to a dot product of 0. But we'll practice that more in the future. Okay, a couple more things with the dot product quickly before we move on is that this idea of the Cauchy-Schwarz inequality just tells us this. Basically, if I take the dot product of two vectors and I take the absolute value of that, because remember this is a scalar, that's always going to be smaller than the product of the vectors of the two magnitudes or lengths of those vectors separately. So let's look at this. Well, first of all, you guys know that the dot product is just this. So if I plug that over here, imagine for a second. The only difference now between this side and this side is this addition of cos theta and obviously the absolute value. So what does cos theta do to this number? Well, cos theta can only give me something from -1 to 1. So if I multiply by a -1 or a 1, it's not going to change it because of the absolute value, right? Even the -1 would just keep it the same. That's the equal to part. Otherwise, cosine is going to give you some fraction between there, which would make this smaller than it already was. Hence, it would have to be less than or equal to. So pretty easy to prove that idea. The last one is this idea of triangle inequality, which basically says if I take the magnitude of a sum of two vectors, it always has to be less than the other two, the vectors added separately. So this is this idea, guys. Like if I have two vectors, I'll have this be A and this can be B. And I add them together. Remember, we can add them using like the head to tail method. So there's me adding B. Here, orange is the result, A plus B. So what I'm saying is that these two vectors, if you were to add them separately, so like if this had a length of 5 and this had a length of 3, this vector here, this orange vector, has to be 8 or less. In fact, the only time it would be 8 is if those two vectors A and B, 5 and 3, were headed in the exact same direction, then giving us a total of being 8. Okay? So, and of course, if that's the case, technically, if they're going in the same direction, they wouldn't be making a triangle at all. So we said that's like a degenerate triangle. So basically, this third side has to be less than the sum of that to create an actual triangle. Okay. Okay, so let's move on to some new applications that we could be doing to apply this. There's something coming up that we're going to be using called a projection of a vector or projecting a vector onto another one. And that's going to help us be able to develop some relationships between vectors and lines and vectors and planes. And so we need to talk about what it means to be a projection. So I've got a lot going on up here, but I'm actually going to do it using kind of a diagram. I think you guys will be able to understand that a little bit better. So okay, so I'm going to project vector A onto B. Okay, so imagine that this is my vector A, and this is my vector B. Okay, so just like you might think of when I ask you, you know, like what's a projector? Where's an example of something you project, you know, maybe in the real world? People might say, you know, like if I project a video onto a wall or a video onto a screen, right? Like the idea of a projector. That's the same thing that's happening here. You can think of the one you're projecting onto, just like the wall you might be projecting onto, as your wall, as your vector. So you can think of it as a light source. Like, so I'm going to kind of think of it as like there's a flashlight up here. It's my flashlight today. And that flashlight is projecting light onto or directly at B. Okay, at the one that I'm projecting onto. So this light source is projecting straight at the wall or straight at B. And the projection of A onto B, guys, is literally just the shadow. So this thing I'm drawing right now is not the shadow. That's just me showing you it going straight down. And it would meet that there at a right angle. Now the actual shadow would be this teal vector right here. So this right here is the projection of A onto B. Now look at the way I wrote that. The projection of A onto B, you have this subscript of B. That's the one you're projecting onto. This is the one that's projecting. So this teal part, this shadow, is the projection. Okay? Now, projections can be positive or negative. The way this one would be positive because the projection is headed in the same direction as my vector. to just show you quickly what it would look like if it wasn't, I might have vector B, and perhaps I've got A headed in this direction. So again, that light source is headed from above directly onto B, and so now you'd have you'd have to extend B in the opposite direction, and now your shadow would be here. So this would have a negative projection value, whereas this would have a positive projection value, if that makes sense. Okay. And again, it is a scalar. This length of projection is a scalar. The sign or the parity just again tells you, indicates the side that it's headed. Okay, so let's say that we were trying to find this projection, and I'm going to use this diagram. This is just a little more friendly. So we have a right triangle. Let's talk about what we know. Well, if we want the length of this projection, we do know the length of A because we should have that vector, and we technically know B. So, okay, if we know the length of A, and we know this is a right triangle, well, imagine for a second that we knew this little angle here. Just imagine with me. If I knew that angle, then I would know if I wanted to use this length and find this length, that would be adjacent, and hypotenuse, which would be the cos of theta, because it's a right triangle, right? So I'll just put projection of A onto B. Okay. Over, and we're talking length here, so the length of this projection. Okay, over the magnitude. So this is, again, just adjacent over hypotenuse. So then if I finish doing this and multiply by the denominator, I end up with this. So this is equal to my length of my projection, or that shadow, right? Okay, so the cool thing is, we've got that up here as well. If I don't have the angle, then I need a way to kind of get rid of or replace this cos theta with something I know. So what I did is I multiplied the top and bottom by a magnitude of B, which shouldn't change it. Like if B is 5 long, then multiplying the top and bottom by 5 shouldn't change my answer. But it allows me to replace this with something we've already learned today. Magnitude of A times B times the cos of the angle between them, boom, is the dot product. So that's pretty cool. So if I want to know the length of that shadow, all I need is the dot product of the two vectors and to divide by the magnitude of vector B. Wow, that's awesome. So I actually don't need the angle in between, we found out. So that's why I said, imagine you know the angle for a second, because you actually don't need it later. Okay. Now, we can find this actual vector, like if we wanted to find the actual vector, this is only its length right now. If we wanted to find the actual vector, we can do that, and we might talk about that later. We'll get into that, but for now, that's the length. Okay. All right. Okay, I did also say I would do a brief talk about the dot product being a part of something defined as work. So definition of work is that work equals the force vector. So the work done by a constant force. So for example, PQ, as the point of the application moves along PR, is called the dot product. So it's the force vector times the direction, or dot the direction vector, right? So if you've done this in physics, you've probably seen this before. So again, the work done is the force vector dot the direction that you're headed. So again, see, this one says like the point moves along PR. So like if I had PR, here's my little dot, and it's going to move, you know, along the line, and maybe I'm using a force to pull it of PQ, and so I could talk about work. Okay, but we can see that in the book. Okay, so for the second half of this little video, I'm going to turn to something, like I said, completely different for a minute, but I promise we'll come back to projections here in a moment. So, okay. So we're going to work in 2-space, and then I will show you this in 3-space, obviously, as well. If you want to take a break before you start the second part of the video, it might be a good moment to just walk away and come back. But I'm going to keep going, so feel free to pause and come back if you need to. All right, so, okay. Consider a line in 2-space. Beep. Write it in standard form. So standard form, great. Eventually I'm going to switch to something called a front-loaded version, which would basically be when I set it equal to 0, so I also bring the C over. So that I will deal with that in a minute. Okay, so what we want to do is determine the form that a position vector, that just means it starts at the origin, that's perpendicular to the line and pointing towards the line will look like. So like I basically want this little guy. See this little guy down here? It's headed from the origin. It's going to be headed towards the line. It's going to be perpendicular to the line. And so this is my little picture. So, okay, here's my standard form of my line. If I did change this line into slope-intercept form, this is what it would look like. Like I literally subtracted the AX, divided everybody by a B. I think everybody's fine with that. Okay. So, all right, well, let's think about what we would need this vector, this little vector right here to look like for it to be perpendicular and headed towards the line. Okay. Well, you guys might be able to tell me a little something about the vector, right? Because we would want this direction to be perpendicular to the line, and you can get the slope of the line from this equation, right? Okay, so the slope of the line is negative a over b, where this a and this b refer to, and some of you might be more comfortable with the standard form, you know, looking like this, so we could also do this. So you know that the slope of this line is going to come out to negative a over b. We've talked about that tons of times. That's just something that you should be very comfortable and aware of. Okay. If we want a perpendicular vector to that line, then I want the slope to be perpendicular. So I'd have to flip it and take the reciprocal, or I'm sorry, take the opposite reciprocal. So that would become a positive b over a, right? Okay, so that would mean that the change in y would have to be b, the change in x would have to be a. Okay, so that would look like this vector. So my vector would need, I don't know why this b is attached there, so that shouldn't be, sorry. So that means my vector would have to be in the direction of AI, because that's how much I remember. The bottom is change in x, and the top is change in y, right? So this should be how much I move in the y direction. This should be how much I move in the x direction. Okay, so everybody, I think, is okay with that. Okay. Okay, now the vector could point in the opposite direction. Like, how do I know that this A and this B isn't going this way, right? Because you could also have a vector that's perpendicular. This is important. Your perpendicular could also have been flip it, and then maybe you made the B negative as well, right? Like the top could have been negative. So you can have a vector that goes in that's perpendicular that's also, you know, has a negative B and a negative A. So it could also look like that. Right? Okay, so we have two different versions of vectors that could be perpendicular. Again, what I mean by that is, here, I'll do it in red. You know, maybe my perpendicular vector, instead of going that way, is going this way. But they're both perpendicular, right? And they both start at the origin. So we have to consider both of those in a moment. Okay, first of all, these little vectors that have relationships to these lines, if they're perpendicular, we call these normals, meaning we say, like, these vectors are normal to that line, meaning perpendicular. That's huge. I'm going to refer to normals a lot coming up. So, okay. So do you guys see any interesting relationship between the normal to the line and the actual line? There is a pattern. Look at this. The normal is A in front of the X and B in front of the Y. Hey, just like the A was here and the B was here. So yeah, there's absolutely a pattern, guys. The pattern in this particular relationship is that your normal vector ends up being the coefficients of the standard form of the line, right? Okay, so let me write that down before I get into this bottom part. So once again, if you want a vector that's perpendicular to a line, that's in standard form, that's important. So ax y plus, equals c. If I want a vector that's perpendicular to that, that vector would just be AB. AB is perpendicular to that line. That's huge. Or, of course, you could use negative A, negative B, because these two things are parallel. Okay. So if we have two different normals to a line, then how do we know which one we want in a given setting, right? Like, how do we know if I want to be this normal that's headed maybe towards my line or this normal that's headed away from my line? You know, like, that might be important. Again, it usually doesn't matter, but if it does, and we want the normal vector that points towards the line, okay? So again, this is called the positive normal, that's real important because you're going to hear me say positive normal. Positive normal is again the vector that's perpendicular and headed towards the line. So that would be like this blue vector. It would have a positive normal. It's perpendicular and it's headed towards the line from the origin. Okay. All right. So that positive normal, and again, I said if the line actually goes through the origin, then neither of them would point towards the line. So there would, you would just have a normal in general. All right, so let's get some rules so we can figure out how we know which one's pointing which way. Which one do we want? Which one is technically the positive one? Okay. All right. All right, let's consider these two parallel lines. So here's my two lines, my two purple ones. And so their slopes are the same. I think I wrote it a little weird, but this is the slope here, right? Okay. So my slope is like 5/3 plus 4. So see, it goes through 4, and then it's going up 5/3. This one is going through -3 and then up 5/3. Okay. So those little values out front are kind of like my little vectors. They're parallel. Now, if you'll notice, I have from the origin, I have a line that would be perpendicular to it from the origin, and I also have a line that's perpendicular from the origin but to the other one, right? Now these technically, the orange and red line are technically perpendicular to both, like it doesn't matter which, but only one of them would go towards that line, and only one of them would go towards this line. Like the orange guy isn't going to go towards that line. Okay. I also have the standard form of both equations here, right? Now, if you're trying to figure out which one is which, this guy, 5x minus 3y, you could solve this pretty easily and get that this guy is this one. So this is the 5x minus 3y equals 9, and this is the 5x minus 3y 12, negative 12. So those are just written that way. Okay. So my normals, let's go back to that. If I wanted the normals, notice these have the exact same A and B because they're parallel. The normals to those would be, I wrote them down here, 5, -3, AB, and then also the opposite, so -5, +3. Both of those would be normals. Here they are in basis vector form, here they are in component form. Again, it's fine to use either version. I got that just by doing AB. So those have to be the normals. Now, you guys can tell which one of these is which just by looking at the picture. So like, let's see, which one of these is the 5, -3? Orange or red? 5, -3 would have to be this orange line, right? And -5, 3 would be would be this red one, right? -5, 3. So for this guy, the positive normal is 5, -3. For this guy, the positive normal was actually the opposite one, -5, 3. So any thoughts on maybe how or what we could use to decide which one would be the correct normal? Maybe you caught the pattern. If the C value is positive, you're going to use the positive normal will be A and B directly. If the C value is negative, then you have to flip them to get the positive normal. So one more time, if you're looking for the positive normal to the line, if C is positive, then you can just use A and B. If C is negative, then it would be the opposite. So I think I have this on my next page, yeah. So if you want to ensure that you have a positive normal vector as in A and B, just make sure that C is positive. So if it's not, force it to be positive, right? So like, for example, if I have the equation 2x minus 5y equals -10, and I want to make sure that I use the right normal, I could just multiply everybody by a -1, force C to be positive, and then my normal to that line would definitely be -2, 5. I could also get it from here by saying, oh, this is negative, so I have to switch them, -2, +5. But so it's up to you, okay? All right. So that's how we get normals to lines. Now I will tell you that sometimes we need our normal vectors to be a certain length long, in particular, sometimes 1 unit long. So if you need your vector to be a particular length, guys, so here comes my little vector. If I need that vector to be a particular length long, it's easiest to go down to a length of 1. So let's just say, for example, let's say that that my normal vector here, my purple vector, is 4, 3. okay? What is the magnitude of n then? 4 squared plus 3 squared, square rooted 5. So if I want to be able to move a particular distance, it would be easiest if I first scale that down to a length of 1, which is called a unit vector, right? Okay, well, how did I do that? If I want to scale this down, I have to divide each of the components by 5, by the magnitude of the whole vector. So you're basically scaling it down to a similar triangle where the hypotenuse is 1. So you've done this before, so we need to take our vector down to a unit vector. And now we have something called a unit normal. So this is nice because then if I want to go like 3 in this direction, I can just multiply this guy by a scalar of 3, and I'll move a distance of 3. Okay? So unit normals, super important. We're going to use them in a little bit, and they're going to move us along this perpendicular distance. Okay. Okay. This is me already saying you basically just divide the vector by its magnitude, so I already did that. Okay. Already did that. Okay. So I said in a moment we're going to get some interesting formulas that will allow us to determine how far a point is from a line, the shortest distance from a point to a line, which would be perpendicular. But first, I just want to make sure everybody's fine with a normal vector to a plane. So we just said that a normal vector for a line, if you have the line in standard form, was just, A and B. So the normal vector was AB, or negative A, negative B, right? The normal vector to a plane, which you guys actually already know this. We've been using this now for a little while. If you want a vector that's normal, we said, if you remember, that it's the same as the coefficients for the plane. So this is where that comes from, guys. This idea of being normal, this idea of having these coefficients. So again, if you want a vector to be perpendicular to a plane or normal to a plane, then it's going to have the same A, B, and now C values from the coefficients for the standard form of a plane. And if you wanted to make sure you had the positive normal, we're going to do the same thing. This time we're going to look at the D value. If the D value is positive, you're going to use ABC. If it's negative and you want a positive normal, you use negative A, negative B, negative C. If you want a unit normal, you would just divide this by the magnitude of that vector. So it's the same thing for 2 space. I was just converting it to a 3 space for you. So okay, so like I said, fasten your seatbelts. On the last test, I asked you to find out how far a point was from a plane, and in 2 space we did points to a line. And if we think about what we had to do to solve that problem, here's a quick one. We would write an equation for the construct that was perpendicular to and containing the point. So like in 3 space, for example, I would write an equation for if I had, let's see, so here's my point, maybe here's my line. If I had to find something that was perpendicular. So in 2 space, I would find like the line that was perpendicular, and then I would intersect those two things together. If I was in 3 space, I would have to do the perpendicular plane, remember this, and then which took me a minute, and then I would find the intersection of the plane and the line, and then I would have to find the distance between those 2 points, right? It wasn't terrible, but I said, we wish we had a more efficient approach to find the distance between a point and a line, or again, in a moment, a point and a plane. So let's take a look at how we could do that. All right, so we have our line here. Here's my standard form of that line. I have my point out here that I'm given. So this is the point that I'm going to try to find the distance from the point to the line, okay? So this whole length is the distance. I know that the distance will have to be the perpendicular. That's the shortest distance. That's what I mean when I say distance from a point to a line. And I have a couple of things that I know. First of all, I know if I take a normal vector from this point towards the line, then that would be headed along that distance. You might also recognize that the distance from the point to the line is just the absolute value of the projection of this purple vector onto this vector, okay? So that is also the length there. So if I were to project the purple vector, P1 to P, onto my normal vector, so if I were to project that, so if you can't see what I'm talking about, here's your little light source, right? My little light source is shining towards my normal vector, so I'm going to project the purple onto the green. If I can get that projection, it is longer than the normal, but that's fine. It doesn't matter. Sometimes your shadow's longer. So then this whole shadow would be the length of the projection, which would be that distance. And again, if I use the absolute value, then I would get that whole distance. So that's my plan, guys. That's huge. It's a really big deal. Okay, so number one, let me get rid of that. So first, we need a couple of things. So we would need the vector that's going from P1 to P, and it has to go in that direction. So P1, so it would go from the point to a point on the line. So we could pick any point on the line that we would want to. Okay, so that would be that vector. We know that the normal to this line would just be AB. Okay, we didn't worry right now about whether that normal was positive or negative, because it doesn't end up mattering, because the projection is going to be the same length whether the projection had a negative value or a positive value, because remember, we're just going to take the absolute value anyway. Okay, so let's take a look at this. So we said we know we can get this by projecting it. Well, let's go back to what we know about the projection. So the projection of this guy onto the normal vector, if you remember, is going to be the dot product of the two vectors, pink, green, the dot product of those over the magnitude of the one that you're projecting onto, right? We did this earlier in the video, okay? We're projecting, I'm going to write this off to the side. We're not in yellow. We're projecting P1P onto the normal. So it's that order. So remember, that is the dot product of those two vectors over the magnitude of the one you're projecting onto its magnitude. Okay. All right, so let's break that down. So that would look like, all right, well, the projection here, and again, we can pick any point. So I just filled that in with this could be any point on the line. So I left it x, y. So we've got this, change in x, change in y. We've got my normal vector over the magnitude. The magnitude of n, the normal, is pretty easy. If n is just this, it would be a squared plus b squared square rooted. Okay, so I'm going to scroll down. So I'm simplifying this a little bit here. This just becomes this, when I do, remember, when you do the dot product, it's just this one's x times this one's x, boom, plus this one's y times this one's y, boom. And again, this is all over the magnitude of the normal. Again, I have the absolute value because I just want the length. Okay, so then I started putting some stuff together and isolating some stuff. What do you notice? Oh, this is ax plus by. That has a relationship to my c value, so I plugged in my c value. Now, again, this won't matter whether it's a positive or normal, which is why I can use the negative c here, but we can always talk about that later. So I replace this with a negative c. When I replace that with a negative c, I can take a negative out of everybody, and because it's the absolute value, if I have a negative inside of an absolute value, it becomes positive anyway. So I went ahead and changed that. And then this is over that. This is huge, guys. This is our result. So this was all just me showing you how to get there, which you don't necessarily have to do. This is the big, big, big piece. So what did we just learn? We learned that the distance from a point to a line can be found by doing, okay, now this is important. Remember, AB is the normal to the line, okay? So there's your A and B. Your x1, y1 were the x and y values of your point. So the point is x sub 1, y sub 1. So look what I did here. I've got A, B, C. I don't know if you guys noticed, but that whole top is just, this is just the equation of our line, but it's with the C brought over. That's why that negative C is there, by the way. So this is our front-loaded version of our line. We'll do this, an example of this in a second. Over a squared plus b squared. And then look, the x1, y1 is just the point that was plugged in. And then again, it's the absolute value. I know that's a little crazy, so I'm going to do an example of it, I think, next. Let me go to that slide. Yeah, I'll do it here. So let's try this. Let me do an example for you. So let's use the line. We'll do 4x plus 3y equals 12. And I'll graph that guy. I picked this for a reason, so that the x and y intercepts would be nice. So my x-intercept is going to be a 3. My y-intercept is going to be a 4. Okay, so there roughly is my line. And I'll pick a point that I know for sure is not on the line. So maybe I pick the point like -2, -1. Okay, so I've got the equation of my line. Now I'm going to front load it so that I can use it appropriately according to my model. So again, if I front load the equation, and by front loading I mean just bring it over and set it equal to 0, okay? That means that the distance from here to this line, this distance, is equal to the absolute value of, okay, so we said it's the front-loaded version of our line, right? A, B, C, over the normal. So we needed the normal. These are actually parts of the normal, but the normal to this, and again, it didn't matter if it was positive or negative, would be 4, 3. So 4, 3, we already knew that, but it's the magnitude of the normal. So it ends up just being these same values. So basically, it's the magnitude of the a squared plus b squared. And then our point. So we're plugging in our point, -2, -1. So our distance ends up being, let's see, we've got -8, -3, -12, all over 5. So I end up with, what do we got here? -23/5, which comes out to 23/5. So the distance between this point and this line is a length of 23/5. Pretty crazy, okay? We're going to talk about how you can figure, how you can decide, like if I had another point, if it was on the same side of the line or the opposite side of the line, but that will come later. Okay. Okay, so we can do one more example. So let's do -2x plus 5y equals -20. Okay, so that line, let's see, my x-intercept would be 10, and my y-intercept would be -4. Okay, so there's my line. So I could even use the point 0, 0, guys, if I wanted to, if I want to know how far the line was from 0, 0. So once again, that distance from the point to the line, I'd front load my line. You can front load it on either side, so it doesn't matter if you take it to this side or that side. I'll go ahead and just bring everybody to the left because I'm comfortable with that. I do that mostly, and I'm going to use the point 0, 0. So because you're using 0, 0, when you go to plug in your line, the only thing that ends up affecting it is actually that C value because, you know, these guys end up coming out to 0. But the -2 and the 5 are important for the magnitude of the bottom. So I get +20 over, let's see, what do we got? Root 29. So there's my distance between my point and my line. Okay, cool. Okay, so I can do the same thing in 3 space if we're interested to know how far a point is from a plane. So again, you have a plane, you've got a point hovering above, you know, how far would that distance be at the point from the plane? Okay, so once again, guys, I think without having to do a long version, we can say it's the same idea. If I were to put a point out here in space, and I were to take a vector and connect the point to that point out in space, and then I were to project it onto this normal, it's the same idea. I'm projecting towards that. Here's my little light source projecting out there. This projection onto this would again give me the distance from the point to the line. So, same deal. It's the same exact thing. If I do that front-loaded version of my plane, and I use my arbitrary point, and I'm just going to go through this quickly, I can do all that same work, guys, and I get the exact same thing. The distance from a point to a plane ends up being, check it out, here's the equation for my plane. So just like I had for my line, except this time it's my plane with my point plugged in. X sub 1, y sub 1, z sub 1, all over the magnitude of that normal vector, which again, the normal vector is a, b, c. So we've got a squared, b squared. So it's the exact same thing as 2D. I'll remind you of the 2D version here. The 2D version is a line, so ax1 plus by1 plus c all over a squared plus b squared, square rooted. So again, this is my 2D version because it's a line. This is my 3D version because it's a plane. And this will get you the distance from a point to a plane. Okay, my recommendation is just to memorize this first one. And then, of course, all you need is really if you know the equation for the plane, you can notice that the A, B, and C, again, for the plane are those values for the bottom. If you are doing in two space, then you can just get rid of the C in both and think of the D as like the previous C, right? So then you only have to really remember one relationship. I also said if you're finding the distance from the origin, remember that the X, Y, and Z would all be 0, which basically gets rid of that. And so you only really need that last constant value to solve it. You can just kind of do it a little quicker that way. So, okay. Like I said, another thing to remember is that while the length of a projection can be negative, the distance cannot, because distance technically is always absolute value. So just realize that your answer should come out to positive values because we're doing the absolute value around it, right? Okay. Um, Again, if we measure a couple of distances and we wonder whether the 2 points that we're using, so like, if I gave you the equation of a line and I gave you a couple of points, if we want to know if the points are on the same side or on opposite sides, so like I'll call this A, B, and C, um, we have about a 50% chance, 50-50 chance of getting it right, right? But if we want to actually see where the points lie with respect to one another, we can try those out. So what I would like to do is you can maybe try some of those and see if you guys can come up with a way. Maybe ask yourself that. How can you use the distance formula? And you can do it either from a point to a line, or you can also do it from a point to a plane. The relationship will be the same. How can you use that to help you decide whether 2 points that you choose, so you'd have to have two, how can you decide if those 2 points are on the same side of your line or plane, or they're on different sides of your line or your plane? So that's what I want you guys to think about. And we can answer that in a Zoom session. But give this a shot and see how things go. I know that this was a long video, so please, please, please feel free to go back and watch things. And thank you so much for listening and staying with me. And good luck with all of the problem sets. Okay, bye.